Good morning and welcome. My name is Michael Wentz. I work for Accenture Technology Labs in the Data Insights R&D group. For those of you that are not familiar with Accenture Technology Labs, we're the forward-looking R&D group of Accenture. We're located here in San Jose in downtown, but also other 4 locations geographically. Now, when enterprises start to and decide on deploying Hadoop, they ask themselves this very question: where to deploy Hadoop, bare metal or cloud? When we're trying to answer this question, there's 4 deployment models that we typically look at. The first being on-premise full custom. And what this is the commodity hardware being purchased by the business, installing the software, complete customization and control over the business. Taking a little bit step back from the technical configuration, we have the Hadoop appliance. Install that into your data center, you can quickly jump-start your analytics without all the technical configuration. Transitioning outside of the traditional corporate data center, we have Hadoop Hosting. So this is the traditional ISP model where you're having Hadoop hosted, configured by a service provider. And then lastly, on the cloud side, we have Hadoop-as-a-service, which is Hadoop on-demand, instant virtualized clusters. And it's usually a pay-per-use consumption model. The nice key thing about this here is businesses are able to have greater agility and flexibility. So for our study, we focused on the ends of the spectrum. We focused on the bare metal and the cloud side. Now, when you're trying to choose which of these deployment models, what key areas do you look at? The first is price-performance ratio. Given a limited IT budget, how do I maximize my ROI? With bare metal, one of the biggest problems that we have is a very high upfront infrastructure cost. Cloud, you don't really have the high upfront infrastructure cost, but you do have a lot of greater flexibility and scalability. Data privacy, obviously when we start taking information outside of the corporate data center and placing it into cloud, there are some concerns there. And bare metal does give you a better peace of mind and security in this regard. Data gravity, now we start talking about, we're all here, we're talking about big data, right? So we're going from gigabytes to petabytes to terabytes. And as you increase your scale and size of data, it's very hard to physically move the data between different data centers and clusters. So it really makes sense for us to look at the future of the cluster. Where are we deploying this? How much data are we going to be ingesting? What do our workloads and the time frame look like? Does it make sense to do something smaller because we're not really looking at much now, and then maybe change to a different deployment model and do something larger later? Which kind of goes into data enrichment. So in data enrichment, we're combining multiple data sources to drive better insights from the data. A really cool example of this is consumer transaction data on one hand, and then you have social network data for the same customer on the other. By themselves, they start giving you a picture of what the consumer is interested in, what they like, but together they give you much greater insight and value for the business when you combine them. Now this kind of goes back into data gravity, because since you're having multiple data sets, do you host them in the same cluster, in the same deployment? Should one be separate from the other? Then there's also geographic location considerations as far as if it's powering an application. And lastly, we look at the productivity of developers and data scientists. This one here is definitely a lot easier to do in the cloud, since you're going to want your data scientists and developers to think outside the box. You might be looking at a few key metrics here or some areas, but you want to be able to expand on those models, look at the other data. So being able to create a sandbox and be able to work in that environment, it is available. You are able to do it in bare metal. It's just typically a little bit more cumbersome. So for our study, we focus on the key area of price-performance ratio. Now, when we talk about price-performance ratio in Hadoop, there's 2 distinct and divergent views. The first one comes from the bare metal side, where Hadoop is a very I/O-intensive workload. So if we're adding a virtualization layer, we're going to have some slowdown. However, on the cloud side, we have the, basically, like it says, who cares, I'm cheap. The instances, virtualized instances, are cheaper than their bare metal counterparts. So even if there is a problem with the virtualization overhead, we can just add a couple more virtualized nodes to the workload to be able to get the same performance. Which brings me to the Hadoop deployment comparison study. So in this study, what we do is we compare the price-performance ratio between bare metal and Hadoop-as-a-service. And we do this at the matched total cost of ownership level. And then we combine it with the Accenture Data Platform Benchmark, which is a set of real-world applications that we've used from our internal research and studies. Let's first start with the Tco analysis. For the Tco analysis for the bare metal cluster, we took small-scale initial production deployment, and we modeled that on 24 server nodes with 50 terabytes of HDFS capacity. This is using a replication factor of 3. Just before I go a little bit further, the numbers I'm about to show you here, as far as how we came about them, the depreciation models we're using, that's all in the full white paper, which feel free to reach out to me afterwards and we can share that. So I don't want to go too deep into it, but we have to start thinking about these 4 areas when we're trying to consider TCO analysis. The first is server hardware. How much is it going to cost for us to buy and maintain the server hardware? The second area is the data center. If we're doing a bare metal deployment within a corporation, we're going to need some place not only for the servers, but we also have to pay for the electricity that powers the servers. Third area is technical support. Now, this is usually provided by third-party vendors such as Cloudera, and lastly, staff for operation. So if we're thinking about bare metal, we're going to have in-house people that are dedicated just to the operation and management of this cluster. So when we start thinking about how much this is going to cost on a monthly basis, we come up with the numbers that are here on below for each respective category. And if we sum them together, we get $21,845.04 per month as our TCO budget. Now, we're going to take this budget and we're going to apply it to a Hadoop-as-a-service because we're going to be doing a fixed budget for both. So this is how we're going to be able to calculate the number of affordable instances. First, we still have staff for operation. In this case, it's fewer staff because most of the configuration and the maintenance is done and provided by Amazon Web Services in this case. Technical support is provided by AWS Premium Support, which most closely matched what third-party vendors on the bare metal case have. Now, if you notice here on the last slide, I had data center electricity. Well, since we're operating in a virtualized environment, we actually need storage services. We need a place to actually house our data when we're not running it in the virtualized Hadoop clusters. And for that, we're using Amazon S3. And lastly, it's the Hadoop service itself, which is Amazon Elastic MapReduce, or EMR. So again, if we start with the $21,845, and we start subtracting these 3, we end up with about $15,300 for Hadoop as a service. Now that is how much we can actually allocate to the Amazon EMR instances. But when I'm talking about instances, how many instances are there? Well, it turns out that there's 14 instances with 3 pricing models. So if we do some quick arithmetic, we have 42 combinations. Obviously, it's time and cost prohibitive for us to try, for this study, to go through and evaluate every single one of them. The way that we address this is to go through and select 3 representative types. So M1 extra large, M2 4 extra large, and CC2 8 extra large. The reason why we selected these was because when we look at them, they're the largest of their column, they're the largest of their instant family types. And also, Amazon provides a couple instances that are very high storage capacity, such as like 20 terabytes on a node, or there's other ones that have very high CPU but very low memory. So those didn't really quite map to what you typically expect in a Hadoop node. And for us, now that we have selected these 3 with the 3 pricing options, we now have 9 combinations that we're going to use. But the question then becomes, what is the affordable instance count? So to determine this, we made 2 assumptions. The first is 50% cluster utilization. So what that means is over a 24-hour period, we have only about 12 hours of the day we're using the Hadoop service. And then a third of our budget is allocated for spot instances. And I'll come back to that point in a second. So if you recall, we have $15,318.28 for this budget. So how do we allocate it? So between our instance types, we have 3 instance types. And then we also have the 3 pricing schemes. So the first one is the on-demand instances. And for anyone that's familiar with the way Amazon Web Services works, on-demand instances is typically the highest cost per hour to use. And then reserved instances is a reduced hourly rate, but businesses sign up for a contract, an upfront contract for a year, 2 years, 3 years, depending on how long they want to use this service. Then the last one is reserved plus spot instances. So really in the Amazon model, it's on-demand, reserved, and then spot. The reason why we only allocated a third for spot budget here is we had two problems that would usually happen. Since the spot instances are so much lower cost than the first two, we could get very large pools of instances. But then when we try to go into Amazon to satisfy that request, we'd end up driving the prices up so high that we'd end up biting ourselves because then we're not saving any money and we're not able to afford those instances anymore. Or there was another situation where we would try to lock in, we were able to actually get it, and then the next thing we know, all of our machines are shutting down because somebody else went into the same pool with a higher bid price and were outbidding us. So to address that, what we did was take the reserve pricing for 2/3 of the budget for this last one on the right, and then only a third for the spot instances. So now that we've gone over the TCO analysis, let's switch gears and talk about the other part, which is the Accenture Data Platform Benchmark. So what it is a suite of real-world Hadoop MapReduce applications. Like I was saying earlier, it comes from our client experience, our internal roadmap, and public literature. So how did we decide which use cases and workloads to use? First, we categorized and selected the common use cases. And then to actually implement them, we used open source libraries and public data sets. The use cases and workloads that we came up with was log management as the use case, which mapped to the sessionization workload, customer preference prediction, which mapped to recommendation engine, text analytics, which mapped to document clustering workload. So let's just take a quick look through what each one of those workloads entailed and the data size and data sets that we use. First is sessionization. So pretty much session is a bunch of related events that it's very useful for us to analyze as a group. You want to think about security analytics, website optimization, network optimization. This is usually where sessionization comes into play. So we take the log data as our input, we do bucketing, sorting, and slicing, and our output are the actual sessions. For our data set, we had about 150 billion log entries, which was about 24 terabytes of data. Now, this was generated from 1 million distinct users, which created about 1.1 billion sessions. Now we have also the recommendation engine, which is another one of our workloads. And basically, we were using an item-based collaborative filtering algorithm. We use so the Mahout library has an example recommendation engine. We use that as a base or foundation and built on top with this algorithm. And basically, we take the ratings data, we create a co-occurrence matrix, and then from the two, combining the two, we're able to drive out a recommendation. For this, we use 300 million ratings, and it was a unique 3 million population with about 50,000 items that we were doing the recommendations off of. The last of our workload for the benchmark is document clustering. So this was the most resource-intensive workload that we had. We had nodes that were failing, running out of memory. There's a lot of bits and pieces to this. If I recall correctly, it's 10 to 12 cascaded MapReduce jobs. So basically, we're trying to group similar documents through here. This is used in a lot of similar techniques, like as it says, search engine, e-commerce site optimization. But first, we had to grab the corpus of crawled web pages, filter, tokenize those documents, take out like punctuation, stop words, move into the term dictionary creation, combine the two to create a term frequency vector, so how often does a particular word occur in a document, and then we created term frequency, inverse document frequency vectors, which basically says, you know, if I have dog that's in this particular document, is it very relevant to that document? Does it not appear in the corpus? So it's some way that I can categorize the document, because if I have 10,000 documents and dog only appears in 5 of them, that's a very good way for me to say, obviously this is a way that I can categorize that document because it's very unique. And then we use k-means clustering to produce the clustered documents. So we use the Common Crawl dataset. It's publicly available on Amazon S3, and it was a 10 terabyte corpus, and that was uncompressed. Compressed, it was about a little over 3 terabytes. Consisted of about 31,000 Internet Archive files from crawling the web, and it was about 300 million HTML pages that we processed. So we've talked about the Tco analysis. We've talked about the Accenture Data Platform Benchmark. So how do we bring it all together for our actual experiment of study? Let's first start talking about the setup, and then we can go into the results. So for the setup, as we were saying before, we're comparing one bare metal cluster with 9 Amazon EMR clusters. And again, to reiterate, instead of trying to match performance one for one, what we're trying to do is take a fixed budget size and determine the size of our cluster based on that. We're measuring the execution times of the benchmark. And lastly, we're doing manual and automated tuning. So let's focus on the last bit here, the manual and automated tuning. For the automated tuning, we actually use Starfish, which is now Unravel, and it's an automated performance tuning tool for MapReduce jobs. So for our study, what we did was we ran each benchmark twice. We ran it once because there's a profile phase for Starfish, which basically sits there, collects data and information about the MapReduce job, then takes that information to go into the optimize phase. From the optimize phase, it tunes the cluster parameters more appropriately for the workload that is running. And lastly, just as a clarification, the measure of the execution time that we were looking at was actually the optimize phase, since that was we usually had a very good speed up in between the profile and the optimize phase. So let's talk about results. Let's first start with Starfish. So how do we compare automated versus manual tuning? Well, we use Starfish on the recommendation engine that we talked about. Now, this workload is about 11 cascaded MapReduce jobs. And what was really interesting was the first time that we used the Starfish tool, we were able to get an 8 times performance increase. And this was from the default settings on the Hadoop cluster. We didn't change anything. We just ran it through a profile phase and then an optimize phase, and this was the result. So obviously, that's very significant. But we needed some sort of comparison. So we wanted to manually tune the sessionization workload. Took over 2 weeks of manual tuning just for us to be able to get where we were happy with it, and we're like, okay, well, we can't tune it any further. The biggest challenge and issue here was it took about a half to 1 day for every single iteration. If you think about it, if the job runs for 6 to 9 hours, you can do it when you're at 5 o'clock, you launch it and you go home. But as soon as you come in the morning, you're doing log analysis. You're trying to find out what happened. I tweaked this parameter. What was the result? Did I get less spill? Hey, did I run out of memory on my nodes by looking at ganglia? And it's a very involved, not only in time, but also resources. You have to have an engineer that is very familiar with these performance tuning results, and also the MapReduce architecture. So the merit of Starfish here is to be able to achieve performance increases with much less cost. And it's not only cost in time, but also resources. If you think about a general business, they're not going to have a MapReduce expert or an engineer. It's mostly going to be business analysts that are running either Mahout queries. So these performance tuning tools help cut down on the amount of expertise needed, but also give you the added benefit of being able to utilize your cluster more efficiently. So here is the actual one of the results from our sessionization workload. All of the graphs are going to be exactly the same, so let me explain it. Over here, we have the execution time for minutes, and then we have 3 clusters of the bars. Each cluster represents our pricing models that we're using. So all the way on the far left, we have the on-demand instance pricing, the reserved instance pricing in the center, and on the far right, we have the reserved plus spot instance pricing. And the colors match the distinct instance types. So we have orange for M1 extra large, M24 extra large green, and blue for CC2 8 extra large. Now at the top, you see the red line there with the note that says bare metal 533. So that red line is what represented for our runtime on bare metal. That's just about 9 hours it took. So the fastest, or excuse me, the slowest running Amazon EMR cluster was able to finish that about 2 hours faster than the bare metal. So does this mean that we don't need bare metal anymore and cloud is so much better? Well, this starts opening up the idea that we can actually tune the clusters, our cluster size and configurations based on the workload. If you take a case in point for the on-demand instance, even though it's one of the higher cost ones, for M1 extra large in the yellow bar here, we have 68 instances that are running. We get really good performance time. It's actually just 4 hours and 10 minutes versus 9 hours. So that's a big performance increase. But maybe our business rules are that we only need 9 hours. So there's no reason for us to spend all of this money to be able to get that performance. We could actually decrease the number of instances, save money in our budget, and still get the same performance that we're getting on bare metal. So if we go to the recommendation engine results, this is the first time that we start actually seeing the bars peak over the red line. But if we take a look, bare metal completed about 21.5 minutes. The first one here in the reserved instance, the CC2 extra large, 8 extra large, was maybe 30 seconds slower, and then the on-demand CC2 8 extra large was about 2 minutes slower. So it's not a very big difference. But for the same cost that you would have a bare metal cluster, this is the performance that you can expect. And again, as I was saying earlier, we can go through and tune all of our settings and cluster configurations for the particular workloads. And one thing I think is interesting on here is if you look at the yellowish-orange bars for the M1 extra large, you can kind of see like an increase. And the reason why you see kind of a little bit of an increase in time is you could put all the nodes that you want out there, but if you have certain places in your MapReduce framework where it's a fixed number of reducers or a fixed number of map jobs that are being used, even though I have 10,000 slots, if I'm not filling them, then that's capacity that I'm wasting and I'm not utilizing. So even though between the on-demand I had 68 instances, then I go to 112 and 192, I don't see a big benefit in this workload because it can't take advantage of all that extra capacity. And again, this goes back to how can we tune the jobs and the infrastructure to support the workloads that we're trying to run. And lastly is document clustering. As I said before, this was the most resource intensive of the 3 workloads. For the bare metal, it took about 19 hours. If you look at the first 2 bars all the way over, for those of you that don't remember how many minutes are in a day, it's 1,440. So those 2 took over a day to complete. And again, that's not to say that Hadoop-as-a-service or cloud is not a good fit for these particular workloads. It's just those particular instance types are not necessarily, or the instance types and the number of instances aren't really the right combination that we should be using. Because again, we see here with M1 extra large, we're actually able, with the 68, we're actually able to get a very good performance increase. But you also have to keep in mind that's 68 virtual instances that have 8 map slots apiece and 3 reduce slots apiece. So the ability to be able to ingest all that corpus, those 31,000 Internet Archive files that I was talking about, is expanded by being able to have such a very large ingest path. And another thing that you see here too is when we go from to pick out M1 extra large again, when we go from 112 to 192, obviously that was a big jump in capacity. But again, we don't really see a very big performance increase. We only see maybe like 30 minutes. And the reason for that is because there were some very intensive reduce jobs, reduce operations that were running that had a fixed number of reduce slots. So even though we're adding all this extra capacity on the reducer side and also the map side, you might be able to run quickly through a job that's very map intensive for ingestion, but once you hit the other parts that you're relying on the reducers and there's 50 of them, then the extra capacity is actually going to waste here. And from a business side of things, why should we be spending the extra money for a very large cluster when it's not actually giving us the performance increase that we're looking for. So it brings me to my key takeaways. So, excuse me, Hadoop-as-a-service offers a better price-performance ratio. The benefit of performance tuning is so huge that the cloud's virtualization overhead, the cloud's virtualization low overhead is a worthy investment. And as we saw through the results, it helps expand the performance tuning opportunities. So not even getting to the point of where we're talking about like automated performance tuning tools, we can actually have the cluster hardware appropriately configured for the workload and the jobs that we're trying to do. And then if there's like document clustering, since we saw how resource intensive and how long that took, we can easily, in the cloud, appropriate more instances to get through those humps, those speeds, those processes that it's taking a very long time to ingest. We can say, here, for the next 2 hours, you have 20 extra nodes to be able to help you get through that. And when we're thinking about bare metal, usually the typical investment by businesses is 3 years out. So if we do 24 node cluster, yeah, Hadoop is horizontally scalable. We can take advantage by buying new hardware, but it's a very huge capital expense for most businesses. And lastly, automated performance tuning tools are a necessity. Whether you're a business analyst or a developer for MapReduce, these tools help get you more, help you to get more ability out of the Hadoop cluster. You don't want to be using the Hadoop cluster all the time. If you can make it from 9 hours to 4 hours, even in cloud or on bare metal, you're unlocking 4 hours of time to play, try new ideas, or even run different workloads. So you're able to drive that cluster utilization of 50% up higher to closer to 100%. And of course, I would like to acknowledge Metascale. We were working with them, and they provided our bare metal platform that we were testing on. Amazon Web Services provided the Hadoop-as-a-service for us to do testing. Cloudera worked with us on third-party vendor support. And then lastly, Unravel, who was able to work with, who allowed us to use their Starfish tool for the performance testing. And of course, Accenture for providing the funding for this study. So as I was talking about earlier, the Tco Analysis has a lot of information as far as how did we select the cluster size that we selected, what is the depreciation value, how do we come up with the numbers that you saw in the presentation. That's all available in our full white paper. You can either contact myself, and that's my contact information, or Scott Kurth, who's our group lead for data insights at Accenture Technology Labs. We'll be happy to discuss this with you. I do have about 50 copies of the executive summary up here if anyone's interested. We just had them printed this week since the paper was finalized. But if anyone has any questions, there's the microphones there.
So the server nodes, that you were using?
I think, 1 second, I think he's turning it on.
So, there you go. So the server nodes that you were using for the bare metal cluster, how did they compare to the 3 types of cloud servers that you used, the cloud instance that you used?
So they had about 24 gigabytes of memory. So if we think about M1 extra large, it has 15 gigabytes of memory, if I recall correctly, that's allocated to it. So obviously there was a pretty big disadvantage, especially when we're using document clustering, because it was so memory intensive. We'd actually have to tune the parameters on Amazon EMR differently than we did on bare metal, because when you had all the mappers start and you're getting close to the end and you're about 98% done, if you have slow start on, then the reducers kick in. But if you're on EMR and you only have 15 gigabytes of memory, and you have 8 map tasks, each of which takes 1.5 gigs, that's already 11 gigs there. And if you have 3 reducers that try to start up for 4.5 gigabytes, you're already over your 15 gigabyte limit. And we had nodes that would crash, so we'd actually have to turn slow start and make it that 100% of all the map tasks would actually have to stop, or like complete fully before the reducers could start. So that definitely was one of the things that, as far as just at least those 2 instances trying to compare between memory, that was a big challenge that we had when we were trying to run the benchmark, just because, like I said, the nodes would just die, and you just started getting all these Java heap errors, out of memory errors, and it was it's definitely a little challenging, but we were able to overcome it. And then for the other 2, like the M2 4 extra large and the CC2 8 extra large, they're around 60 gigabytes, I think, of memory. So we really didn't hit that ceiling mark that we did with the M1s. Yep.
So you have, so you have.
I think he wants you to use the one in front. Thank you.
So you've actually 2 things you are coming up with. One is the cost one, and the second one is the performance. So on the performance, the question is that is my understanding the reason is actually faster or nearly as fast as bare metal is because you are actually for the same price able to allocate actually more resources.
Right, that's correct.
That's the only reason why it can possibly be faster, right? So the one about the cost, so clearly if I'm a customer that is running an application occasionally, no-brainer that running it on the cloud or Hadoop-as-a-service makes sense. What would have been interesting is if you had actually maybe taken your 3 applications and said, I'm a customer that is running actually not just one application once in a while, but I have actually now, my business is starting to use Hadoop more regularly. And what would be interesting is if you were to take multiple applications where you get your utilization on the bare metal up to over 50–60%, and then compare it also while running all those 3 also in the cloud. And there will be another one because for a number of customers, they're kind of moving towards not just one application once in a while towards Hadoop. You have a lot of data that you now constantly, regularly use on and on.
Right, and we're seeing a lot of, like you're saying, instead of just the typical like nightly batch job that only runs once a time, you're starting to get in a situation where you're having that nightly batch job, but it's accompanied by a streaming data source that's being continuously processed in smaller batches. So definitely the landscape is changing. We started this study back in July of last year, so that definitely is a good point.
So with the change, you think the price performance recommendation model as you start running a load that is fairly constant, or are you planning to do that as a next study?
I'm not, actually at the moment I'm not sure, but it is a good idea. As far as like how the prices would change, I still think that cloud has an advantage, at least for the fact that you can tune them for the specific workloads, especially in the fact that you can move from where you're limited to, it depends on each business case, but if you're limited to like a 24 server node cluster, yes, using MapReduce 2 like Yarn, you get more flexibility of being able to use the resources of the cluster, but you're still kind of locked into their scale. There's still a wall there. Where with cloud, you can start off very small. If you need to go aggressive for a few days, weeks, months, or even years, you can, and that infrastructure already exists without having to have all these capital resources and investments up front with bare metal.
Okay, and you didn't include in your price the cost of transferring the data, right? Into Amazon.
So in AWS, it's free to bring data in.
Okay.
It's cost to take it out. To take data out.
Okay.
Yeah.
Yeah, actually that led into my question. So in this study, have you accounted for the performance and the cost which takes to load data into cloud and maybe bring data out of cloud?
So since the data, most of the data sets that we're using were either generated or available in Amazon S3, we didn't look at those particular aspects, but you're right, with ETL, there is definitely not necessarily, well, since it is free to import it into the cloud, it's more of a time cost to be able to, and infrastructure to be able to pipe that data in. But Amazon has a lot of services where you can actually either get a very fast pipe into your data center to be able to upload information, or I'm not sure if they discontinued it, but I know at one point they had a place where you could actually just ship them arrays of hard drives and they'll import it into the cloud for you. So you don't have to take the weeks or months to be able to transfer your gigabytes and terabytes of data.
Okay, so it's safe to assume in this study all the data was assumed to be sitting in cloud, right?
So it was local to wherever it was. So for bare metal, we did not pull the data, all that common crawl data that we use, we did not pull it directly from S3 as we were using it. To make it a fair comparison, we actually downloaded all of the data over over a week to the bare metal cluster, and it was there sitting locally in HDFS. That way, it was fair for both since they're both locally pulling it.
Okay, thanks.
Welcome.
Hi. My question is for k-means clustering, did you use the Mahout library? Or?
Yes.
Okay.
Yeah.
The second question, a quick question is, where can we get more details on the cluster configuration for bare metal?
So in the white paper,
Okay,
it actually has the bare metal cluster configuration. As far as the specs, you have to forgive me, I don't remember all of them off the top of my head at the moment.
That's okay, I get it.
But as far as the server model, how much memory, CPU, and then also for AWS, you can easily go on AWS for the 3 instances that we used, and it has all the configuration
Right,
settings.
thank you.
You're welcome.
Hi, my question is about the Amazon instances. The cost is also a function of time that you use it. So when you hardware doesn't have that. Once you buy it, you incur the cost. So when you calculate the price of Hadoop services, did you calculate such as when you turn off the run, you don't count the cost anymore? Or you just run, say, 192 instances continuously for the whole time, even though when you don't use it?
So we assumed 50% cluster utilization over the entire month. So we just said, okay, for 1 month, or for half a month, how much can we afford to run 24 hours a day, or how much can we afford to run 12 hours every day? And that's how, so basically this is, with that amount of utilization, it's basically assuming that you would come up, do your batch job, do the workloads you need to, and then go back down so you weren't continuously running. Or maybe you are continuously running it for 2 weeks, and then you're not running anything for 2 weeks.
So what do you think if you compute the cost just based on, like, I need to run it 9 hours a day, and then I turn it off. So I only use it 9 hours a day, which is like 1/3 of the cost. Would that be cheaper?
So if you're only, then this amount of money, this would actually go down. I mean, it would go down in the sense that you wouldn't be utilizing that full budget. If we go back a few more slides, and we talk about the key areas. So here we have staff for operation technical support. So the technical support is actually based on how much you use Amazon. So this might actually decrease as well, because if you utilize it less, you might be in a cheaper support model. Storage services, also, that's variable, but the storage services here is to match the storage capability, the 50 terabytes that we were able to have on the bare metal cluster. And staff for operation, if you remember, so this is 3,000, almost 100, but if we go back to the other one, it's 9,000 here, and the reason why there's a big difference is because we're assuming that you're going to need 3 full-time employees for the bare metal cluster, where on the Hadoop-as-a-service, you're only going to need 1 full-time employee. Just because Amazon's taking care of a lot of the configuration and maintenance, they have service nannies, if you will, that if a node accidentally gets stuck, hung up, non-responsive, it'll actually kill the node off, bring in another one. So a lot of these tasks that you would have to have a full-time person monitoring the cluster and making sure things are working well and supporting the developers and data scientists. With the cloud model, we only assumed that you needed 1 just because of all of the services that Amazon gives.
Thank you.
You're welcome. Well, thank you, everybody.